Okay, here is some work I've done on the data from when we mounted kuka on a crane over Nilus ice. Here's a picture of it. The ice was very smooth, but in clear flows, and there was a little bit of swell coming in from open water to the right. So the flows were just gently moving relative to each other. So that definitely complicates the situation because small cracks of open water were sometimes forming, as you will see in a minute. I'm just going to restrict this video and the analysis I've done so far to Ka band and also mostly focus on HV polarization, but towards the end of the presentation there's some VV as well. I also just focused on one less than a minute period where we lowered the radar down by about 6 meters. So the antennas went from 8 meters height, as you'll see on the left of the screen, to around 2 meters height, and that corresponds to when the actual runners of the sled were only about 40 centimeters above the water. You can see here that there's like a harmonic side lobe that I'll talk about later. But you can see what's going on really from this main peak here, this like high energy part of the echogram. So it starts steady, and then we drop the crane, the radar's lowered down towards the water, and then it hits we stop it going down at about 5, 10 and 20 seconds, and then it just sits that level. So here's a video of a camera that we mounted on the Ka band horn. So it gives you an idea of what the radar saw, although it's important to note that the angle of the camera is kind of looking back annoyingly at the sled a bit. So you see a lot of sled here, whereas of course the actual antenna horn can't see the sled. That would defeat the point. Hopefully you can see that there is a crack here between the two Nilus flows where there's maybe some open water, and there's a bit of a roughness induced by the sort of almost pancake edges of these plates of ice. Okay, so these peaks that you can see in the echogram, that like bright green peak, they look like this. And for all the peaks, to work out what the max value of the peaks is, I've drawn a high order, like 13th order polynomial through the data points to work out the position and maximum height of the peaks, rather than just picking the range bin with the largest value. Doing this also allows me to accurately calculate the full width at half maximum. That's FWHM, as you can see in the annotation here. So to do that, I just work out the maximum value of the peak, and then I halve it, and then I work out the width of the peak between at that half maximum Y value. So we can do that for every radar shot during this descent, which is about 170 radar shots, and we can look at how the width of these peaks and the power of the peaks varies with range, and how the power varies with the width, and all of that stuff. So let's get into it, I guess. The first observation is that there's no clear relationship between the width of the peak on the y-axis and the range of the peak. So it appears that as kuka gets further away from the ice, the peaks don't actually get noticeably narrower or wider, which is interesting, I guess. However, there is a relationship between the full width half maximum, the width of the peaks, and the power of the peaks. So it appears that you only get these really powerful peaks when they're really narrow, and you only get these really wide peaks when the power is really low. And then we also have this like bunt clustering of points down here, so most of peaks are actually weak and narrow. Here's the power of the peaks plotted against the range. So you might expect for like a spherically expanding wavefront that you get a 1 over r squared value. 1 over r squared relationship, and you do kind of get that, but you also get this slightly mysterious like chaff of points down here that ruins the relationship a bit. And the obvious question to ask there is this due to tilt? Are we distorting a nice clean 1 over r squared relationship due to the tilt of the instrument? And I'm going to talk about that now. So here is the tilt of the instrument during the period in which it was descending from 8 meters height to 2 meters height, in 0.2 of a degree bins. I calculated the total tilt from the across track and the along track tilt. The reason it's 5 degrees, quite consistently 5 degrees actually, I'm quite pleased that it's not swinging around wildly, is that I was holding a rope attached to the tip of a ski to stop the radar from spinning around, and that's kind of unavoidable, to keep a little bit of tension on the sled from using a rope attached to the bank at all times, because otherwise it just spins round, and I think it would actually swing significantly. So I think by inducing a small constant tilt, we avoided swinging, so the inducing of variable but sometimes large tilt. But it does clearly vary, and there's like a decent chunk between 4.8 to 5 and a decent chunk between 5.4 to 6. So one thing to do, therefore, if we want to see if this relationship will improve by controlling for tilt, is to just look at the tilt in a narrow band. So why don't we just look at the data 0.1 degrees either side of the mean tilt, and that's what's represented by this orange band here on this graph. And when we do that, we do seem to get a better 1 over r squared relationship. That's what that red line is. It's a fitted inverse square curve. So that's encouraging, I guess. Here's just a summary graph of what's going on. There's no filtering out of tilt or anything, but it just kind of would be a neat plot for someone to display. You're all welcome to it. I'll link to these slides in the video description. I guess it's good to talk about side lobes. So that's what's in red here. You can see this is HV, KAHV, and you can see 2 harmonic side lobes. So here there's the main peak corresponding to the ice at about 2 meters range, and then there's like another phantom peak, and then actually sometimes you can see another phantom peak here. And I'm going to call those harmonic side lobes. And the reason I'm going to call them harmonic is because take that first phantom peak, it's generally at double the range of the antennas from the ice. So when the antennas are far away from the ice, at 8 meters, the phantom peak shows up around 16 meters, and then as the antennas get closer to the ice, down to about 2 meters, the phantom peak goes to around 4. So it's always double, and that's kind of a good thing because we're not going to confuse it with geophysical features, and that's fine. I guess what we should be worried about is peaks that emerge at like constant range relative to an interface, and that was somewhat infamously a thing for Operation Icebridge, where there was a big old side lobe above the ice surface, I think, that they persistently initially misidentified as the snow surface. So that's the danger here. If we just go back to this echogram actually and consider the waveform corresponding to this first column and this last column, I'm going to plot those on the next slide. So first we'll show the echogram of the radar at 8 meters, and then secondly we'll show the echogram of the radar at 2 meters. You can see there's obviously a main peak here, a big main peak for both, and then afterwards there's like a second subsidiary peak, 10 to 11 centimeters deeper than the main peak. And you might think, oh, maybe this is an intriguing sort of cross-polarized signature from the bottom of the ice. And that's what I initially thought. We can, rather than just examining 2 waves, we can actually examine all of the waveforms produced by the descent by normalizing the power. and plotting on the x-axis like relative to that main peak. So I've just popped out of my little zone here, but basically that's what it looks like. First, I want to jump back in. I've been thrown here, and say, is that the bottom of the ice? Well, we can actually tell using a video where we later used the sled runner to break the ice to try and see how thick it was. So there you go. That's a little video of it breaking, and you can see. There we go. The ice there is probably not 10 centimeters thick. So when we're looking at these subsidiary secondary peaks here that indicate it is 10 centimeters, I'll grant you that that's in radar range, so maybe it's like 8 centimeters in real range when you consider slower propagation. I think that probably doesn't respond to the ice surface. And in fact, when we plot all of the waveforms like this, we see that there is persistently this peak that probably doesn't correspond to the bottom of the ice, and when we average these waves we get this like side lobe, something that I'm fairly confident to describe as a side lobe. And the interesting thing about this one is it's not a harmonic. It doesn't move relative to the main peak with range, so that is obviously quite interesting because 10 centimeters is a plausible snow depth. So yeah, something to think about there, I guess. I guess also you might argue maybe it's not a side lobe, maybe it's like an off-nadir snag from a quote-unquote lead, like a little tiny gap between the ice. But I think the fact that it appears at all ranges from 8 meters to 2 meters, and over that range of ranges the footprint size changes quite a lot, implies to me that it's not a snag, it is a side lobe. Let's turn to VV. Everything I've shown so far has been HV. VV is kind of interesting in this regard because we see those harmonics, and we also see like a fixed side lobe. So we've got the main peak here at 8 meters, and then we have a fixed side lobe that's persistently about 1.8 meters further away than the main peak. Again, kind of interesting given what we've just discussed. And interestingly, the harmonic side lobe also has this like fixed offset, almost like a side lobe of a side lobe. I don't know what's going on there, but fortunately we know that at these ranges it's not physical, but kind of interesting. And we can perform the same analysis in VV, and we find that we don't see nearly such a persistent or dangerous side lobe in the copolarized channel. So here's that average. There is a little like nub here at 0.3 or so meters, sorry, 0.03, like relative to the main peak. But I don't really think we're in danger of confusing that for like a geophysical feature. It would be a pretty dubious analysis that appealed to that nub as some kind of like feature. So yeah, that's what I've been looking at so far from this crane analysis. Haven't even touched the KU data yet. We also have data from this crane session doing a sweep where we kept the antenna at 2 meters height and swept it over the ice surface, over different flows. So that might be kind of interesting because we can see with the camera when the radar is over more or less of those open water cracks, and we might see changes in the backscatter. We also have a crane exercise from the other end of the runway by the wharf, and that was over small pancakes, maybe 20 meters in 20 centimeters in diameter, but there was swell, and that swell does complicate the issue significantly, which is why I've just focused on the Nihilus case to begin with. And then we also have a whole other situation down by the wharf where we used the crane to scan ice that was flowing under on the tide, and we have some radar shots of different types of ice. So there's lots to do with this crane data. If we're really thinking about side lobes, the next thing to check will be the metal plate shot that we took near the time. And that's what I'm going to do next.